Okay. All right, so let me go back to. All right, so, okay. So this, as I recall, is the last thing we did. So now we're going to talk about some quantitative aspects of the kinetic molecular theory. We didn't really discuss it, we touched on it earlier. But just to remind you, the kinetic molecular theory is a model that is used to explain all that we have discussed with respect to how gases behave, in particular, how we can explain the gas laws, right? So what you're looking at here on the screen are some of the principal assumptions of the kinetic molecular theory. The first one is that gases are made up of molecules that are in constant random straight line motion. Second one is that molecules of the gas are on average far apart from each other. So therefore, basically, if you have a gas in a container, it's mostly empty space. The third one is that there are no intermolecular forces that exist between the gas particles unless they collide with each other. The fourth one is that you will have molecules gaining or losing energy when they collide with each other. However, the total energy remains constant. And I think the term that they use in physics to describe this, we say that the collisions are elastic. So let me put that in parentheses down here. Collisions are elastic. All right. So that's basically okay, so those are basically some of the assumptions of the kinetic molecular theory. So as a result of all that, and I won't go through all the details as to how this equation is derived, but based on what we just discussed, we can derive this equation right here, which shows you the relationship between different variables as far as gases are concerned, right? And just to let you know what each of these terms are, P is the pressure of the gas, N is the number of molecules, V is the volume, M is the mass of each molecule, and then this here is called the average of the squares of the speeds of the molecule. So what this is saying, and in fact, let me write this down here just to make sure you understand what this is all about. U squared bar is equal to the speed of gas 1, which is U1, plus the speed of gas 2, plus the speed of gas 3, and so on until you get to the nth gas molecules. And I should say these represent the speeds of the molecules, not just gases, but the molecules. All of that divided by the total number of molecules, N, all right? So that's what this term means. It's basically the average of the squares. I forgot to put the squares. These should be squares. These should all be squares, all right? So it's the average of the squares of the speeds of the molecules present in a gas, all right? So that's what this means, right? So basically this equation here gives you some relationships between different terms. For example, N is the number of molecules, P is the pressure. So basically we can see that there's a direct relationship between the number of molecules and the pressure, right? There's also an inverse relationship between the pressure and the volume, which is Boyle's law, all right? M is the mass of the molecules, and of course, this is the average of the squares of this, the squares of the speeds of the gas molecules, all right? So basically we can, make some inferences in terms of what pressure is dependent on. So for example, the greater the number of molecules, the greater the pressure. The heavier the molecules or the greater the mass, the greater the pressure. The greater the speeds of the molecules, the greater the pressure. And the greater the volume, the lower the pressure. So those are just some relationships we can identify. Let me just say that you don't need to know this equation, but you should understand that this equation comes directly from the kinetic molecular theory. And then there's another equation which comes from the equation I just showed you, which shows you the relationship between the kinetic energy, the average kinetic energy of the molecules, and the temperature. And there's some other terms here, but these are constants. R is the molar gas constant, and Na is Avogadro's number, and then you have this fraction here, 3/2. But the thing I want to point out here, based on this equation, is that there's a direct relationship between the temperature of the gas expressed in Kelvin and the kinetic energy. So as stated here, the average translational kinetic energy of the molecules is directly proportional to the temperature in Kelvin. So that's another relationship that you need to be aware of, all right? Okay, so let me talk about molecular speeds, all right? Now, as you can imagine, right, if you have a gas trapped in a vessel, you're going to have different molecules having different speeds, all right? So not all molecules will have the same speed. Some will be traveling at a slower speed, others will be traveling much faster, all right? So basically, we can calculate what is called the root mean squared speed, which is basically representative of the average speeds of the gas molecules, right? And the root mean squared speed can be calculated this way. Now, if you remember, I talked about 2 slides ago, I said that the average square of the speeds would be equal to this plus this plus this, and so on until you get to the nth molecule, right? So when they're talking about the root mean squared speed, they're talking about the square root of this, which is the square root of all of this right here, all right? So basically what they're talking about, and I forgot to divide by n here, very important. So what they're talking about here is you square each speeds of each molecule, you average them, and then find the square root of that. And that is called the root mean squared speed, right? And it turns out that there's a relationship between the root mean squared speed of the gas and the molar mass, and it's given by this equation that you're looking at right here. The root mean squared speed is equal to square root of 3RT over M. Now, what are these terms? Hold on 1 minute, what's going on here? Right? Well, R is the molar gas constant. All right? And let me just say here that in this particular equation, the molar gas constant that you're going to use is 8.31 joules mole over Kelvin, all right? So you won't be using the R that we have been using before, that you're familiar with. Remember this R, 0.0821 liters atmospheres over mole Kelvin. Well, we won't be using that one in this equation. Instead, we'll be using this value right here, all right? So that's one important aspect of this equation that you need to be aware of. Another important aspect is the molar mass must be expressed in kilograms per mole. Typically, the molar mass that you'll be using previously would be expressed in grams per mole. But in this particular case, the units of molar mass must be expressed in kilograms per mole. So be careful when you're using this equation, right? When you're using this equation, you have to ensure that R is expressed as 8.31 joules per mole Kelvin, and M, the molar mass, is expressed in kilograms per mole. When you include those units into this equation, then the root mean squared speed will be given in meters per second. And by the way, the temperature must be in Kelvin, as always, all right? So the temperature must be in Kelvin when you're using this equation as well, all right? And as stated here, typically, the root mean squared speeds would be relatively high, as stated here, the order of 1,000 meters per second. And based on this equation, we can see that there's a relationship between the root mean squared speeds and the molar mass. Basically, what this equation is telling you is that the greater the molar mass of the molecule, the slower will be the molecules. In other words, the root mean squared speed will be lower, provided that the temperature is the same. So you can make comparisons between 2 or more gases. So for example, let's say you have carbon dioxide compared to carbon monoxide, right? And let's say you are asked a question, which one has a greater root mean squared speed, right? Well, you can easily say that carbon monoxide will have the greater root mean squared speed. Why? Because carbon monoxide has a molar mass which would be about 12 plus 18, 30 grams per mole, while carbon dioxide will have a molar mass of 44.01 grams per mole, right? So carbon dioxide is heavier compared to carbon monoxide, and therefore you'd expect carbon monoxide to have a greater root mean squared speed. So on average, carbon monoxide travels faster compared to carbon dioxide, provided that the temperatures are the same. Okay, so I want to show you this graph here because, or these two graphs, because they show you basically how the root mean squared speed is affected by a couple of things. One would be temperature, and the other one would be the molecular mass, or molar mass. But before I do that, I just remembered something. Let me go back to this right here. Again, going back to this equation. In fact, let me erase everything. So, okay. So going back to this equation here, I forgot to mention that the temperature here also affects the root mean squared speed, right? So if the temperature increases, the root mean squared speed increases. And again, that makes sense based on the kinetic molecular theory. When you increase the temperature, you're imparting energy to the molecules, and therefore the molecules will travel at a faster rate. So I just thought I should mention that before I start talking about these graphs. Okay, so let's look at these graphs. Let me explain what these graphs are all about. These graphs are basically plotting on the y-axis the relative number of molecules, and on the x-axis the speeds of these molecules. And as you can see, there are three different gases being represented here with their different plots, all right? So it turns out that when you have these plots, you notice that there's a distribution for oxygen, a distribution here for methane, and a distribution here for hydrogen, right? Now, if you want to determine the root mean squared speed based on these plots, what you'd have to do is look for the maximum point of each plot. So let's look at oxygen. The maximum peak here is right here, and then you drop a vertical line. So I'm going to try to do this as accurately as I can. So if you drop a vertical line down, where it cuts the x-axis, that would represent the root mean squared speed for oxygen. So it's going to cut it about here, right? So this is 500. So I would say this is probably about 400, give or take, right? So the root mean squared speed of oxygen is about 400 meters per second, right? And then in the case of methane, you do the same thing. You drop a vertical line down until it cuts the x-axis. So that's about what? What would you say that is? Remember now, this is 500 right here, right? And this is 1,000 right here. So what would you say this is? What would you say? If this is 500 and this is 1,000, this is what? Would you say that's about 700? 800? Okay, let's say 700, right? And then now, in the case of hydrogen, well, this is kind of easy because the maximum is about here. And this is 1,500, right? So I'm just going to put here 1,500, right? So basically, what I'm going to do is write up here the root mean squared speed for each gas. For oxygen, the root mean squared speed is 400 meters per second. For methane, CH4, we said that is about 700 meters per second. And then in the case of hydrogen, the root mean squared speed is 1,500 meters per second. So we see a pattern here, right? The speed increases as the molecule becomes heavier, because if you look at the molar mass of oxygen, that's about 32. If you look at the molar mass of methane, that's about 16. If you look at the molar mass of hydrogen, that's about 2. So these are the molar masses right here, right? So as you can see, as the molar mass of the gas molecule decreases, the speeds of the molecules increases, right? So that's how we see that relationship between the molar mass and the speeds of the molecule. Okay, now that's a graph on the left. The graph on the right is showing you something different for one gas, and that one gas is oxygen. And basically what you're looking at is how the temperature affects the speeds of the oxygen molecules. So we have the distribution for 273 degrees, and then at 1,000 degrees, and then at 2,000 degrees, right? So in the case of 273, we drop the vertical down here to cut the x-axis, which is the same as what we had before. So this is about 400. And then at 1,000 degrees, we drop the vertical down here. So this is about what? What do you think this is, if I'm doing this accurate? This is 400. 500 is right here, right? So this is about what? 600, let's say. And then here, the vertical is almost at 1,500. The vertical, if you found the maximum. So I would say this is about 1,400, right? So basically, at 273 Kelvin, the speeds average would be 400 meters per second. At, what was it, 600 Kelvin? I'm sorry, at 1000 Kelvin, the speed is about 600 meters per second. And then finally at 1400, I'm sorry, at 2000 Kelvin, the speeds would be, okay, we estimate at 1400 meters per second. So in this case, we see the pattern here where as the temperature increases, the speed increases, which again, is something that you'd expect, all right? So that's basically what these two graphs are talking about. Okay, so let's move on now to this particular concept of diffusion, and then we'll be looking at effusion shortly. We won't spend too much time looking at diffusion. But basically, here's a definition of diffusion right here. It is a process by which one substance mixes with one other or more other substances as a result of the translational motion of molecules. Now, one could look at, or one could attempt to look at the rate of diffusion as it relates to the root mean squared speeds of gases. But it turns out that we cannot do that because, as stated here, the diffusion of gases is much slower than would be predicted by molecular speeds due to the frequent collisions of molecules. So what this is saying is that because the molecules are colliding with each other, we cannot use the model that we were using earlier in terms of looking at the relationship between root mean squared speed and molar mass and temperature in order to make predictions as far as diffusions are concerned, right? This is just basically making the point that the average distance a molecule travels between collisions is called a mean free path, right? And that's pretty much all we're going to say about diffusion, because what I really want to get to is a discussion of effusion. But before we do that, let's look at this interesting exercise right here. So let me explain what's happening here. We have two bottles, one containing concentrated hydrochloric acid and the other one containing concentrated ammonium hydroxide, all right? Now, because they're so concentrated, right? If you open those bottles up, you're going to see fumes coming out from each solution. From the hydrochloric acid solution, you're going to see fumes of hydrogen chloride. And for the ammonia solution, or the ammonium hydroxide solution, you're going to see ammonia coming from the mouth of that particular bottle, right? What's going to happen is that there's going to be a reaction. And the reaction between the ammonia and the hydrochloric acid, or the hydrogen chloride, will be this right here. NH3 gas plus HCl, HCl gas to form NH4Cl, which, by the way, is a solid, right? So basically, you're going to have two gases coming together to form a solid, all right? Now, that's what happens when you put these bottles in close proximity to each other, right? You're going to have the HCl coming from one bottle. You're going to have ammonia coming from the other bottle, and the ammonia and the HCl will come together to form ammonium chloride. But what is observed, and this is very interesting, what is observed is that the ammonium chloride solid will be formed close to the bottle containing the hydrochloric acid, right? So my question to you is this: why is it that the ammonium chloride, which is, by the way, this smoky substance that you see here, that's ammonium chloride. My question to you is, why is it that the ammonium chloride is formed at the mouth of the bottle containing the hydrogen chloride and not near the bottle containing the ammonium hydroxide solution? Why do you think that is? They do combine, but they combine close to the bottle containing the hydrogen chloride and not near the bottle containing the ammonium hydroxide. And you guys out there in Zoom, you can also try to answer this question as well. Why do you think that is the case? No idea? Let me give you a hint. It has to do with the relative speeds of the gas molecules, the relative speeds of these two molecules, the ammonia and the hydrogen chloride. All right, let me give you another hint. Which would you expect to travel faster? The ammonia or the hydrogen chloride? Which one of those two would you expect to travel at a faster average speed? Ammonia, why? Because it has a lower molar mass, exactly. If you calculate the molar mass of ammonia, it's about 17. The molar mass of hydrogen chloride is about 36.5. Okay, so with that in mind, right? Why do you think that the ammonium chloride is formed closer to the bottle containing the hydrochloric acid and not closer to the bottle containing the ammonium hydroxide? Has to do with the speed. As you correctly said, the ammonia will travel faster compared to the hydrogen chloride. So why is it that they come into contact closer to the bottle containing the hydrogen, containing the hydrochloric acid? Any ideas out there in Zoom? Okay, so to answer the question, as she correctly said, the ammonia will travel faster, which means that over the same time frame, it's going to travel a longer distance, right? The ammonia is going to travel a longer distance compared to the hydrogen chloride, which means that when they come into contact with each other, they'll come into contact closer to the source of the hydrogen chloride, right? Because the hydrogen chloride will be traveling more slowly, so it won't leave the solution as quickly as in the case of ammonia. So by the time they come into contact, they'll come into contact relatively close to the bottle, which is the source of the hydrogen chloride, and not close to the bottle containing ammonia. I remember when I was in high school, the chemistry teacher I had at the time, he performed a little experiment using these two same solutions. Let me see if I can recreate a diagram showing what he did. So let me go here. Let me get rid of this. All right, so what he did was that he had a tube, right? And one end of the tube is stuffed with cotton. And this cotton is soaked with concentrated hydrochloric acid. The other end of the tube is stuffed with cotton, but the cotton here is soaked with concentrated ammonium hydroxide, right? And then you wait a while, and what happens is that you see a white circle formed closer to the hydrogen chloride, right? And the reason why that happened is because of what I said before. The ammonia is traveling down the tube at a faster rate, while the hydrogen chloride is traveling in the other direction at a slow rate. So by the time they come into contact at some point, which will be closer to the cotton soaked with hydrochloric acid, all right? Again, that basically shows you that the ammonia travels faster compared to the hydrogen chloride, and that's because ammonia has a lower molar mass compared to the hydrogen chloride. All right, okay, so that's as far as that is concerned. Let me go back to full screen here. All right, so basically, what we just talked about is basically what you see here in this green box. The ammonia is lighter, so therefore they move faster than the hydrogen chloride molecules, and therefore they will come into contact closer to the source of the hydrogen chloride. Okay, so now I want to get to, as I said before, effusion, which is different, and you see the difference in the definition right here. Effusion is a process in which a gas escapes from its container through a tiny hole or orifice into a vacuum, all right? Now, because they effuse into a vacuum, then basically you have pretty much no collisions between the molecules. Well, the molecules that are being effused, because basically they will go into a vacuum and they won't collide with anything else, right? So look at this particular hypothetical situation. You have a box here with two types of gases, right? One whose molecules are heavier and the other one is lighter. And you have a small hole here and they're allowed to pass through, right? So what you're going to see here is that, again, based on the equation that we talked about earlier, the heavier molecules will move more slowly, right? So therefore, what you're going to find after, let's say you allow this to occur for a particular fixed period of time, what you're going to find is that what remains in the box would be more of the heavier molecules and less of the lighter molecules, because the lighter molecules will pass through the hole more quickly, all right? Now, there is an equation based on the previous equation that we talked about, which describes comparing the rates of effusion of two different gases. And it's called Graham's law of effusion. And that law says, 1 minute here, there's a mathematical way of expressing it, and there's also a way of expressing it in words. So this is the law right here in words. It says at a fixed temperature, the rates of effusion of gas molecules are inversely proportional to the square roots of their molar masses. And mathematically speaking, this is basically what Graham's law of effusion is saying. Basically, rate of effusion of gas 1 divided by the rate of effusion of gas 2 is equal to the square root of the molar mass of gas 2 divided by the molar mass of gas 1, all right? So that's basically what Graham's law of effusion is saying. And as you can see here, this law is derived from the equation that we saw before. Basically, what was done is that for rate 1, that is proportional to this equation here. For rate 2, that's proportional to this right here. So if you divide rate 1 by rate 2, you're dividing this by this, the 3 RTs will cancel out, and you're going to end up with M2 over M1, square root of all of that, right? So that's basically what Graham's law of effusion is saying, right? And let me just say that in some textbooks, I'm not sure about the textbook that you guys are using now, but for some textbooks, they tend to use effusion and diffusion as if they mean the same thing, but they're not really, two different things, right? So I just thought I should mention that. So some textbooks, you'll actually see Graham's law of diffusion, which technically speaking is not correct, right? It should be Graham's law of effusion, all right? So just thought I should let you know that. Okay, so based on what we have learned, we should be able to do this question. So this question says, if compared under the same conditions, how much faster than helium does hydrogen effuse through a tiny, how much faster than helium does hydrogen effuse through a tiny hole, all right? So the question is asking basically for you to compare the rates of effusion of hydrogen to helium, right? So what the question, one way of expressing what the question is asking for is basically the ratio of the rate of effusion of hydrogen to that of helium, all right? Now, based on Graham's law, that would be equal to the square root of the molar mass of helium divided by the molar mass of hydrogen, all right? So all we have to do is go to the periodic table and look at the molar mass of helium, which is 4.003. So we're going to put up top here 4.003 AMU divided by the molar mass of hydrogen, which would be 2.016 AMU. So that's the square root. So let's do the number crunching. 4.003 divided by 2.016, and then we find the square root of that. So according to my calculation, this works out to be equal to 1.409, right? So basically the rate of effusion of H2 would be equal to 1.409 times the rate of effusion of helium, right? So to answer the question, how much faster, the answer is hydrogen. The final answer is that hydrogen will effuse 1.409 times faster than helium. All right. And that's basically how we answer that question. All right. Okay. Any questions about this example? Any questions? Any questions? Okay. Moving along. Here's another example. Now, this one says 1% of a measured amount of argon escapes through a tiny hole in 77.3 seconds. 1% of the same amount of an unknown gas escapes under the same conditions in 97.6 seconds. So the question is asking for you to calculate the molar mass of the unknown gas, right? So what I'm going to do first is write down an equation based on Graham's law, right? So I'm going to say that the rate of effusion of argon divided by the rate of effusion of the unknown gas is equal to the square root of the molar mass of the gas, the unknown gas, divided by the molar mass of argon. Now, please note how the question is worded. The question is asking for you, well, the question says, the question gives you the time of effusion for both gases. The question did not give you the rate, right? Rate and time are two different things, right? I don't know if you got introduced to this in any of your math classes or anything like that, right? But basically, there's an inverse relationship between rate of any process and the time it takes, right? The greater the rate, the smaller the time, and vice versa, right? So I could add another thing right here, which says that the time of effusion of the unknown gas is equal, divided by the time of effusion of argon is equal to this right here, all right? So this relationship is what we're actually going to use in order to solve this problem. What the question is asking for you to solve is the molar mass of the unknown gas, right? So the first thing I'll try to do is get rid of the square root sign. And how do we get rid of the square root sign in math? We do what? Square both sides, right? So when I square both sides, I'm going to get the mass of the unknown gas here divided by the mass of argon, and that would be equal to the time of effusion of the unknown gas divided by the time of effusion of argon, all of that squared, right? And then now to get the mass of the unknown gas on one side, that would be equal to the mass, the molar mass of argon times the time of effusion of the gas divided by the time of effusion of argon, and then all of that will be squared. And then we put the numbers in. So the molar mass of argon, again, we have to go to the periodic table for that. And that is equal to 39.95. So I'm going to put 39.95 AMU. And then I'll multiply that by the time of effusion of the unknown gas, which according to the question is 97.6 seconds, divided by the time of effusion of argon, which is 77.3 seconds. And of course, we can't forget to square that. So now we're going to do the number crunching. So the 97.6, we're going to divide that by the 77.3, and then we square that, and then we multiply by 39.95. And according to my calculation, this works out to be equal to, rounded off to 3 sig figs, so that would be 63.7 AMU. And technically speaking, it's asking for the molar mass, so I'm just going to add down here, or let me just put it right here. The molar mass is equal to 63.7 grams per mole. So that will be the final answer right there. All right. Okay. Any questions about this? Any questions? Any questions? Any questions? No questions? All right. So I want to underscore what I mentioned before, right? In this particular question, and you know, when it comes to these questions, let me just say this first. When it comes to these questions, you have to read it carefully. You have to identify whether or not the question is referring to either the rate of effusion or the time of effusion. Very important, right? The rate is basically how fast the reaction or the process takes place, right? The time basically is how long. So if you see the question say something like how long or it takes this long, it's talking about time of effusion. If the question refers to something like how fast right, then it's talking about rate. So it's very important that you understand that when you're reading these questions, all right? And that's important, as you're going to see in some of the assignment questions based on Graham's law. Okay, so now we're going to talk about the difference between ideal gases and real gases. So all along, so far in this chapter, we have been assuming that we're talking about ideal gases, right? Ideal gases are basically those gases that can be described by the kinetic molecular theory, and they obey the ideal gas law, right? It turns out, however, that real gases, gases that actually exist in reality, do not behave exactly in the way described as in the ideal gas equation, right? And there are a couple of reasons why that is the case, right? One of the reasons is that one of the assumptions that we talked about with respect to the kinetic molecular theory is that there are no intermolecular forces between the gas particles, right? That was one assumption that we made in that particular theory. In the case of real gases, however, that's not the case. There's always some intermolecular forces that exist between the gas particles, all right? As a result of those intermolecular forces, the pressure of the gas will actually be less compared to what is predicted by the ideal gas equation, right? Another reason why real gases do not obey the ideal gas equation exactly is that we assumed in the case of ideal gases that the particle volumes are essentially zero, right? In other words, we're saying that the particles, the molecules, or the atoms, their volume is so small compared to the size of the container that they're in, that it's effectively zero. Of course, we know that that's not true, right? As small as the particles are, they do have a volume, and that can also influence the behavior of real gases compared to ideal gases. Now, going back to, well, okay, I thought there's something that's going to come up here. So this begs the question, under what conditions of temperature and pressure will number 1 and 2 become important, right? In other words, under what conditions will these forces or these factors become important, which basically affect how real gases differ from ideal gases? And the answer is this right here, under conditions of low temperature and high pressure. So in other words, if the temperature is low and the pressure is high, then basically real gases will behave rather differently compared to ideal gases. So in other words, if you want a real gas to behave more like an ideal gas, you need two things. You need high temperature and low pressure, right? The temperature of the gas must be high and the pressure of the gas must be low, all right? And okay, so this is the diagram I thought was going to come up here. This diagram I'm about to show you basically illustrates how intermolecular forces between the molecules explains why real gas pressures would be lower compared to ideal gas pressures. In the case of an ideal gas, if you concentrate on this molecule here, well, firstly, let me say this. Whenever pressure is exerted on the inner walls of the container, that's due to the molecules being able to hit the walls of the container freely, right? Now, in the case of real gases, that's the case, because if you look at this molecule here hitting this container here, it is not attracted to any of the molecules surrounding it. So therefore, it is basically unencumbered in terms of its ability to hit the wall of the container freely. In this case, however, because you have intermolecular forces here, that basically will hold back the molecule that is about to hit the wall of the container. So therefore, the force of impact here would be less compared to the force of impact here, which means that the pressure here, in this case, would be lower, would be higher in the case of ideal gases compared to the pressure exerted in the case of real gases. So that's basically explaining the reason why real gases exert a lower pressure compared to ideal gases due to the presence of intermolecular forces in the case of real gases. Okay, so in terms of a quantitative view of these things, we know what the ideal gas equation is already. PV is equal to nRT, right? We're all familiar with that equation. Well, a guy by the name of van der Waals, he modified this equation to accommodate real gases. And basically, this is the equation that he came up with. You don't need to memorize this equation. In fact, I think this equation is available in the packet that I have posted in Canvas. But basically, this is the equation that he came up with to describe the behavior of real gases. So you can see that when you compare the ideal gas equation to real gas equation, you see that there's some modification. You have this term being added to the pressure term, and then you have minus NB added to the volume term right here, all right? And there's some constants involved when it comes to the van der Waals equation. You have this term A, which is related to the intermolecular force strength, and then you have B, which is related to the volume of the gas molecules in terms of liters per mole, right? So basically, the A and B terms are basically dependent on the kind of gases that can only be determined empirically by experiment, right? And I think the next slide is a table which contains information about different gases and their A and B terms, right? So basically, if you want to use the van der Waals equation, then you have to use these constants for these different gases, because different gases have different constants for A and B. Okay, there's one particular, and I'm surprised I didn't see it here. There's one particular graph which shows the difference between ideal. Well, I thought it was here. Oh Lord. Okay, I'm so sorry. I thought it was, and I think it's on my thumb drive upstairs, so I won't even try to run up there and get it. Anyway, that's basically the end of this chapter right here. So basically, now you should be able to complete assignment number, what is it? 5, right? So what I'm thinking is that we could use the rest of this time working on those problems. In fact, let me bring this up here. And I can guide you through these here. Assignment number 5. Oh, that's okay. Oh, wrong class. 2045. Okay, so let's see, where are we? By the way, have you guys been able to do questions 8, 9, and 10? Do you need help with any of those? Questions 8, 9, or 10? Yes, ma'am. Okay, so number 10 says you have a mixture of gases that is made by connecting a 7.50 liter flask containing nitrogen at 2.00 atmospheres to a 13.0 liter flask containing hydrogen at 1.00 atmospheres. So when it comes to these kind of questions, I like to draw diagrams. So let me do that right now. So let me go here. Okay, so let me see if I can squeeze that diagram up here. Or let me just scroll down here. Okay, and then let me do this. Okay, so you have one flask, looks like this. And please forgive my lack of artistic skills. I'm not gifted in that area. All right, and they're connected, right? So let's say we have a tap right here which separates it, right? So this flask contains nitrogen, right? The volume is 7.50 liters and the pressure is 2.00 atmospheres, right? And then this flask contains hydrogen And the volume here is 13.0 liters. And the pressure is 1.00 atmospheres, all right? So that's basically the setup, okay? So the question is asking, what is the partial pressure of each gas? Well, let's, hold on. I'm sorry, what is the final volume of each gas? So think about it. If you open this up, let me go back to my writing thing again, right? If you open this up, right? Then what's going to happen? The gases are just going to mix, right? They'll just flow until they fill the entire volume of the setup. So that means that for the first question, the final volume is simply the sum of these two numbers, this and this. So it's going to be equal to 7.50 liters plus 13.0 liters, and that gives you what? 20.5 liters, all right? For some reason, I'm having difficulty writing using this here, but. So this is going to be 20.5 liters, all right? Okay, so that answers the first question, the A part. Now the B part is asking for the partial pressure of each gas. So the assumption is the partial pressure of each gas upon mixing, all right? So, erase this here. Let's think about what's happening in the case of each gas, right? If you focus on the nitrogen here, I'm just going to write here, for nitrogen. The initial pressure is P1, which is 2.00 atmospheres, and the initial volume is V1, which is 7.50 liters. Right? Now, when you open up the separation here and they mix, the final volume is going to be equal to, as we said before, 20.5 liters. What the question is asking for nitrogen is P2. So what equation comes to mind based on what we have right there? What equation comes to mind? It's a gas law. What gas law comes to mind? Boyle's law, right, exactly. Boyle's law says that P1 V1 is equal to P2 V2, right? What the question is asking for is P2. So P2 is equal to P1 V1 over V2, and then all you have to do is put the numbers in. So P1 is 2.00 atmospheres, V1 is 7.50 liters, and V2 is 20.5 liters. And whatever that gives, that would be the answer. So 2 times 7.5, and then we divide by 20.5. So according to my calculations, the answer will be 0.731 atmospheres, all right? And basically we do the same thing for for hydrogen. Okay, so using what we did above as our guide, what would be P1 for hydrogen? What's P1 for hydrogen? 1.00 atmospheres. What's V1 for hydrogen? 13.0 liters. What's V2 for hydrogen? 20.5 liters. So therefore, we need to find P2. So how do we find P2? Let me do that over here. How do we find P2? For hydrogen, for H2. .00 atmospheres, 13.0 liters over 20.5 liters. So let's see what that gives. 1 times 13 divided by 20.5. So according to my calculation, the partial pressure of hydrogen would be 0.634 atmospheres. So this is for hydrogen, and this is for nitrogen. All right? Any questions about that? Any questions? Okay, so now we move on to the C part. What is the total pressure? That's too easy. What's the answer? Exactly. So all you have to do is add the 0.731. We'll do that here. So let me just do that. Let me do that up here. So P total is equal to 0.731 atmospheres plus 0.634 atmospheres. So let's see what that gives. 0.731 plus 0.634. And according to my calculation, that gives 1.365 atmospheres. And that's it. All right. Any questions? Any questions? Any questions out there in Zoom? You guys are awfully silent. Any questions? Okay. Is it okay for me to clear all this? All right, let me do that now. Let me do this. Let me scroll down. Okay, so do you guys need help with this one? Number 11? You guys okay with number 11, or do I need to go through it with you guys? Going once? Going twice? All right, let me move on. How about number 12? Do you guys need help with that one? Gas stoichiometry. You guys need help with that one? Oh, let me see. Somebody said something in the chat. Oh, Brendan is just saying all good. All right. Let me move down to number 13. So number 13 now deals with what we just talked about today, right? It says in an experiment, it takes an unknown gas 1.5 times longer to diffuse. Now remember I said that, some textbooks use diffuse and diffuse to mean the same thing. So, you have to just deal with that, even though they're not the same. So it says an unknown gas takes 1.5 times longer to diffuse than the same amount of oxygen, which is O2. So the question is asking for you to find the molar mass of the unknown gas. Okay, so let me remind you of the equation that we used earlier, which is Graham's law. The rate of effusion of gas 1 divided by rate of effusion of gas 2 is equal to the square root of the molar mass of gas 2 divided by the molar mass of gas 1. And if we're going to include time of effusion, then basically, remember we said that rate and time are inversely proportional. So here we're going to have T2 divided by T1, right? Okay, so this is basically, what you need to remember when it comes to effusion question. Now, in this particular case, it tells you that the unknown gas takes 1.5 times longer to effuse. So basically, you're talking about times, not rates, right? So this is the way I would set this up. I would say that the molar mass of oxygen divided by the molar mass of the unknown gas, square root. That would be equal to, how am I going to do this? You know what? Let me rephrase or restate this differently. I'm sorry. I would say that the time of effusion of an unknown gas divided by the time of effusion of oxygen is equal to 1.5. And that's based on what the question says here, right? That would be equal to the square root of the molar mass of the unknown gas divided by the molar mass of oxygen, right? So this is basically what you're going to use right here. 1.5 is equal to the square root of the molar mass of the unknown gas divided by the molar mass of oxygen. The aim is to get the molar mass of the unknown gas. So how would you, excuse me, how would you get that from that relationship that you see here on the screen? 1.5 is equal to the square root of the molar mass of the unknown gas divided by the molar mass of oxygen, right? You need to do what? Okay, so we need to get rid of the square root sign by doing what? Square both sides. So we square both sides of this equation. You're going to get 1.5 squared is equal to the molar mass of the gas divided by the molar mass of oxygen, right? And then what? Okay, so when you multiply both sides by the molar mass of oxygen, you're going to get the molar mass of the unknown gas is equal to 1.5 squared times the molar mass of oxygen. What's the molar mass of oxygen? O2. Exactly. So it's going to be 1.5 squared times 32.00 grams per mole. And that's it. So 32 times 1.5 squared, and according to my calculation, this works out to be equal to 72 grams per mole. All right, so that's the final answer right there. Any questions about this? Any questions? Any questions? Okay, so if you understood that one, I guess it's okay for me to clear this, right? If you understand what we just did, then you should be able to do 14. It says, suppose a gas diffuses, and again, diffuses should be the right term, 1.4 times as fast as sulfur dioxide at the same temperature and pressure. What is the molar mass of the unknown gas? So how would you go about doing this one? Basically, you're using the same expression. Now, in this case, the way I would set this up, I would say that the molar mass, well, it's not actually the same because you're talking about how fast. So we're talking about rates this time, all right? So the way I would set this up is that the rate of effusion of SO2, I'm sorry, the rate of effusion of the unknown gas divided by the rate of effusion of SO2 is equal to 1.4. Right? And that would be equal to the square root of the molar mass of SO2 divided by the molar mass of the unknown gas. So what would be your next step? Okay, so when you square both sides, you're going to get 1.4 squared is equal to the molar mass of SO2 divided by the molar mass of the unknown gas. And then what? I'm sorry? Okay, so if you do that, you're going to get mg times 1.4 squared is equal to MSO2. And then what? Oops. It's very hard to write with this thing here. SO2. And then what? Right, I would divide both sides by 1.4 squared. So the molar mass of the gas will be equal to the molar mass of SO2 divided by 1.4 squared. So of course you have to go to the periodic table and you have to add up the molar mass of sulfur, which is 32.47 plus 2 times oxygen, 2 times 16, so that's plus 32. So I got as the molar mass of sulfur dioxide, that would be equal to 64.07, 64 0.07, 7 grams per mole divided by 1.4 squared. And let me see what that is equal to. So divide by 1.4 squared. Okay, so according to my calculation, this works out to be equal to 33 grams per mole. And that's how you do that. All right, any questions? Any questions? Okay. Let me clear this and scroll down. Now this one is just asking for you to compute the relative rates of the fusion of chlorine to krypton. Very simple. Actually, basically what they're asking for you to do is find the rate of a fusion of chlorine to that of krypton. So that would be equal to, according to Graham's law, the molar mass of krypton divided by the molar mass of chlorine. So all you have to do is go to the periodic table. For krypton, the molar mass is 83.80. So we're going to put square root of 83.80 grams per mole divided by the molar mass of chlorine. Chlorine is 35.45 times 2. So that will be 70.90 grams per mole. And then you do the number crunching. So that's 83.30 divided by 70.90. And according to my calculation, this works out to be 1.08. All right, any questions? Any questions? All right, the next one says the velocity of nitrogen is 35 centimeters per second. Determine the rate at which hydrogen sulfide would travel under these same conditions. So in this case, you're comparing the rate of a fusion of nitrogen to that of hydrogen sulfide. So basically, this is what you want to find, right? So this would be equal to the square root of the molar mass of H2S divided by the molar mass of N2, right? So if we want to find this here, that means that the rate of a fusion of H2S would be equal to the rate of a fusion of nitrogen multiplied by, what am I doing? Multiplied by the square root of the molar mass of N2 divided by the molar mass of H2S. And it's a matter of putting these numbers in. So the rate of a fusion of nitrogen is 35 centimeters per second times the square root of the molar mass of nitrogen, which is 14.01 times 2, which would be 28.01 grams per mole. And then in the case of sulfur, that's 2 times 1.008 plus 32.07. And that gives you 34.09 grams per mole. And we work that out. So that's 28.01 divided by 34.09. Then I find the square root of that, and then I multiply that by 35. And according to my calculation, this works out to be 32 centimeters per second. And that's how you do that. All right, any questions about this one? Any questions? Any questions? Okay, let me clear this. Let me do this, and let me scroll down. Okay, so let's see if you guys can do this one on your own without my help. It says here that it took 56.3 seconds for a given volume of chlorine gas to diffuse through a pinhole under given conditions of temperature and pressure. How long will it take for the same volume of diborane, and it gives you the formula, to diffuse through the same hole under the same conditions? So in this case, they're not giving you rate information, they're giving you time information, all right? So how would you go about tackling this problem? And I want to hear from you guys out there in Zoom. Well, only 2 of you out there so far. How would you tackle this particular problem? Well, they gave you the time of diffusion for chlorine gas. And remember, chlorine, by the way, exists as Cl2, very important, right? And they gave you the formula for the other gas, right? And they're asking for the time for that other gas, how long it would take, right? So how would you go about solving this problem? What's the first thing you would write down? Well, if you understood what we have been doing so far, this should be a breeze. Well, what do you guys have to say? Let's start off with this. What would this be equal to? The rate of diffusion of chlorine divided by the rate of diffusion of diborane. What would that be equal to? Okay, very good. And what would that be equal to? Because remember, the question is talking about time. And remember, we said there's an inverse relationship between rate and time, right? So what would this be equal to in terms of time? Very good. Okay, so what next? Let's see if we can do this in the remaining 2 minutes. What next? Okay, so let's see if we can do this quickly. The more, you know what, I'm going to cheat. I'm going to use my molar mass calculator. In the interest of time, molar mass calculator. Come on, come on, come on, come on. Okay, so diboron B2H6. Calculate. So according to the molar mass calculator, the molar mass is 27.67. Okay, make sure you write that down so I remember. And then in the case of chlorine, we did that before. I think that was 79 point, I'm sorry? 70.90, yes, you're right. Okay, so now that we have those two numbers, let me go back to the question. Right, so, oh Lord, let me do this here. Okay, so this part here would be the square root of, what was it? 27.67 grams per mole divided by chlorine, which is 70.90 grams per mole. And that will be equal to the time of effusion of diborane, which is what we need to find, divided by the time of effusion of chlorine, which is 56.3 seconds. So therefore, the time of effusion of diborane will be equal to 56.3 seconds multiplied by the square root of 27.67 grams per mole divided by 70.90 grams per mole. So let's see what that gives. So 27.67 divided by 70.9, and then I find the square root of that, and then I multiply by 56.3. So according to my calculation, this works out to be equal to 35.2 seconds. And that's basically how that is done. All right. Okay, so we have to stop there. Oh, I guess Randy Bartram did it before we did it. She got the right answer, 35.2 seconds. Okay. So yes, Miss Bartram, you're correct. All right. So this is where we have to stop. Make sure you complete this assignment. I'm going to put a deadline for this assignment for Friday. All right. You can upload it online in Canvas. Please, please, please make sure you do so as a PDF document, and make sure you write your name on all the pages. All right. All right. So that's it for today, folks. So I see you guys on Thursday. All right. Take care.